will encounter integer programming problem. That is, your decision variable are integer. So we'll give some intuitive example, and that approach doesn't work. So this is for example from Taylor's textbook in Introduction to Management Science. So we try to maximize something, and we have some constraint, and our decision variable are integers. So we relax the problem. We try to find a linear programming optimal one, and this is our decision variable with our objective function. So there are two approaches. The first one, we try to find nearest solution to the 1. This is 2, and round it to 6. However, this solution is not feasible because it violates the second constraint. The other one is we just round down 2 and 5, but it's a suboptimal with cost. Not cost in this case might be profit. This is our objective function, or we just call it objective function. And actually, the optimal one by using integer programming algorithm is 1/6. So it's 5% difference. So the point is that when you try to use intuition from linear programming directly, it does not work. Okay, so we need to come up with more sophisticated procedure to find our optimal solution for integer programming. And usually for integer programming problem, it's very difficult to solve because you have a combinatorial problem, which is not convex, right? 1, 2, the inner point, it does not belong to the set. So integer programming is not convex. Linear programming is convex. This makes a lot of big differences. But we need to still utilize concept from integer linear programming. It's called LP relaxation. So we treat integer variable as continuous. Why? Because linear programming, we have polynomial time algorithm. So we try to maximize the benefit of linear programming to solve our integer programming problem. So we'll see an example in the later section. We try to transform nonlinear constraint to linear ones so that we could utilize this property. Okay, so this is a slide from Groby. We'll use this software, free software, in our courses. One important idea is called cutting plane. In addition to your original constraint, you add cutting plane. For this one, cutting plane, such that your feasible solution are integer. So when you relax it as a linear programming problem, the optimal solution is integer. So you could find your optimal because you could get the optimal solution from linear programming, and that is optimal because they are integer. So there are systematic algebraic way to do it, and they are developed in 1950 from now. So they keep increasing, keep developing and find better way to efficiently do this kind of thing. The other one is called LP base, branch and bound. And this one goes a long way. At least, I do not check the year, but at least you could check it when it is developed. So the idea is simple. You just, for each region, you just partition it into 2 disjoint branches. Okay. So if one branch is invisible, or that branch is hopeless, for example, the upper bound, the current best one, we try to maximize the best one is 10, and that branch is only 8, the upper bound. So we just discard it. So it's a smart exotic enumeration. You still try to find optimal solution, but in the process, you will discard many hopeless branch. It will save your time. For example, if you had 2 branch, right? And if this branch is hopeless or even infeasible, so you only need to explore the left-hand side, which is only half the original computation. So the trade-off. So we explain the whole picture and come back to the trade-off. So this is the root. You are two different region, right? And the next step, you partition it and find the integer, and this is your upper bound. And if this one is invisible, you just discard this or this part and keep doing it, because you have a different decision variable. So you could find lower bound and upper bound for your integer programming problem. If the gap is 0, you have proof for arithmetic. Or if the gap is very small, for example, 10 to the power minus 6, which is very small in a lot of application. So we just start there. This is the whole idea of branching and bound. You branch and find a bound. So this kind of application is very important. You need to have the basic idea. For example, in you choose the feature or not in a machine learning problem. So the more feature you choose, right, you know, more branch, it will cost you more computational time, even if it will produce more. The quality, the prediction quality is much better. So you need to trade off what is the prediction error, prediction accuracy, and computational time. It's always a trade-off. So we look at the progress of the solver. This is the speed up. This is a famous solver. It's called Cypress. And the later one, a better one come out. It's called Groby. And you keep speeding up using more modern algorithm, cutting plane, branch and bound, and so on. Pre-processing a lot of techniques we won't cover it in our course. This is the total speed up, and hardware speed up. So in 25 years ago, it might take 71 years to solve. Right now, it's only 1 second. It's amazing. It's amazing. And this data is from this breakthrough paper. Use optimization integer programming to solve a best subset selection problem in machine learning. And my lab had to do some work in this area.